Now, if we want to design an oscillator using this single transistor negative resistance, designing a single transistor oscillator, we can redraw the circuit. It just has one transistor and two capacitors. We can see that if we want to design an oscillator, then we can create a resonator where the loss is compensated by this negative resistance. Here, since we already have this capacitor, to create a resonator, we can just connect an inductor. T1, T2. Using this circuit, we can add an inductor. See, this entire series circuit is going to have some loss. That loss we can model as some series resistance Rs. Now this circuit looks like a series LCR circuit where the series resistance is going to be compensated by the negative resistance. So if we draw the circuit using the transistor, to GM. Okay, so we have got a transistor level circuit which can act like a oscillator without biasing. So this circuit, as we can see, that has these three terminals where we can connect appropriate biasing sources. So this is also called as a 3-point oscillator. And here we can very easily calculate the oscillation frequency. First of all, for sustained oscillation, we want that in steady state this Rs to be equal to Gm by omega square C1 C2, and under this condition oscillation frequency is going to be omega naught is equal to, as we can see, this inductor will just resonate with the series combination of C1 C2. It is going to be square root of L C1 C2 by C1 plus C2. So here Rs is modeling loss in this series network. So now we are going to look at various ways we can apply the biasing to this transistor such that this MOSFET is maintained in saturation. Biasing switch. So here we can see that we have the choice of choosing one of these three nodes to be a reference node so as to connect the biasing sources. So depending on which node we choose as a reference node, we can have different biasing circuit. Three choices for reference node to connect biasing circuit. Drain source. Let us take the case 1 where source is reference. If source is used as a reference, say, we can connect a ground or incremental ground to this node. So in such a scenario, what we can do is we can connect a current source from the supply so that drain node sees high impedance. This is gate, source, drain. Now here we can see that the bias current can flow through the transistor with the help of this current source while making sure that drain node is not loaded by the biasing circuitry. We can take the output, the drain, and here we need not show this RS explicitly because RS is capturing the parasitic loss which is present in this network. Now let's see what happens when we choose gate as a reference. Gate is a reference, then we need to connect an incremental ground, and the gate side we need to again ensure there is a path for the DC current to flow in the transistor. And one way to provide the DC current to the transistor is by connecting a DC source at this gate terminal so that it can provide the biasing to the transistor, as well as there will be a path for DC current to come from the drain. And on the source side, we can put a current source so that the source node is not getting loaded by this biasing circuit. And many times we'll see that this gate voltage need not be same as the drain voltage. So we can choose different voltage sources for the gate and the drain. So the circuit can be modified. You can connect a DC source at the gate. Bias the transistor, and at the drain we can connect this inductor L, but now it is coming through a DC supply VDD. And on the source side, we can connect a current source. This is also called as Colpitts oscillator. Now the third configuration is when the drain is the reference node. When we choose drain to be ground or incremental ground, when we can see that we can just connect the drain to the supply itself, it will act like the incremental ground. And for providing the DC path for the bias current to flow, we can connect a current source on the source node. And for the gate biasing, we can remove this terminal of the inductor and use a different DC voltage source to set the gate voltage. So we can use this inductor, connect a biasing source, directly we can connect supply to the drain, and at the source node we can connect this current source. This oscillator topology is also called as Clapp oscillator. We see that in all these single transistor oscillators, basically we have got a different condition for sustained oscillation, and we will find that generally this constraint on the transconductance in this single transistor oscillator is more stringent as compared to what we get in the case of cross-coupled LC oscillator. And also you will see that in all these topologies, whichever way we take the output and do the biasing, the output is always going to be a single-ended output. And many applications we need a differential output, and there are ways to obtain differential output using these 3-point oscillators by using one more replica of this oscillator and trying to couple the two circuits appropriately. Just few points to note about these 3-point oscillators. One, by default, they generate single-ended output. And second point is this GM requirement is more stringent as compared to cross-coupled LC oscillator. To understand the second point where we are claiming the GM requirement is going to be more stringent as compared to cross-coupled LC oscillator, let us try to redraw the equivalent circuit of this 3-point oscillator. Here it is C1, C2, and to be able to compare with the cross-coupled pair, we'll model the loss here as parallel resistance, RP, and this is L. So here the MOSFET is biased in saturation. And let us take a case where this gate is used as a reference. So the gate is grounded. The equivalent circuit is going to be, you have a MOSFET, gate is grounded, and this inductor I am redrawing in this manner. with its loss Rp in parallel. And you can see that this C1 and C2 can be thought of as if they are providing some voltage division for a voltage between drain and gate. So in such a scenario, we can just redraw it as a capacitive divider like this. This is C1, this is C2. And this intermediate node is connected to the source, this manner. And this parallel LCR looking tank is connected to ground on the other side. So both the circuits are completely identical, just that it has been redrawn in a different manner. And these are the ground connection. And this is the output, V out. Okay. So to understand the requirement of GM with respect to this loss which is present in the tank, let us do a simplification where we can find out this voltage which is appearing at the source node of the MOSFET to be just the voltage division of this C1 and C2, and we will be ignoring the loading which is present at this node because of the MOSFET. So there will be some current which will flow in the source node of this MOSFET. Let us ignore that current to simplify our analysis. So if we ignore loading by source node M1, and this is the M1, then the equivalent circuit will become Rp parallel with inductor L with a series combination of capacitor C1, C2, and the MOSFET is having the drain node connected to the tank, while the source node is connected to this intermediate node. And this intermediate node is having a voltage in this simple circuit as a fraction of V0, which is going to be C1 by C1 plus C2 V0. This voltage is also going to be C1 by C1 plus C2 into V0. And we can see that in this tank circuit, if the voltage V0 appears at the output, then there will be a current IR in this parallel resistance Rp, which is modeling the loss. So for a sustained oscillation, we want the current provided by the MOSFET, in our case is ID, to be equal to IR. And if we want this oscillator to start, then this ID should be more than IR at the starting point. And in steady state, because of non-linearity of this MOSFET, we'll find that this fundamental ID component will be equal to the IR component here. So for oscillator startup, we know that ID should be greater than IR, implies ID is GM times the source voltage So this is going to be Gm times C1 by C1 plus C2 V0 to be greater than V0 by Rp, that is IR, implies Gm Rp to be greater than C1 plus C2 by C1, or Gm Rp to be greater than 1 plus C2 by C1. So here we can see that this startup condition is coming out to be more stringent as we got in the case of cross-coupled LC oscillator. There we had GMRP to be greater than 1, but in this case it has to be greater than 1 plus this ratio C2 by C1. So the startup gain requirement is more than that of cross-coupled LC oscillator. Now if we look at this circuit, we can see that here we are using this capacitor to provide the voltage division, and this intermediate node is fed back to the MOSFET source. We can equivalently exchange the roles of inductor and capacitor, where inductor can be used to provide this voltage division. Capacitance will tune out any effective inductance coming out of this inductive divider. So if we do that modification, then the circuit will look like this. Here we have the supply, Rp modeling the loss, C, let's call it L1, L2, and we can connect a current source, the source node for the biasing. And this L1, L2 again can be combined such that we can just take this intermediate node as a tap point in a single inductor to save area. You can take the output here. So this configuration is called as Hartley oscillator. This is similar to the Colpitts oscillator, but you can see that the roles of these inductors and capacitors have been exchanged. So far we have discussed only the oscillators which are designed around the LC resonator. So the role of the active circuit is to compensate the loss in a LC resonator. We will see that there are also other topologies which doesn't require inductor. For example, there are ring oscillators where only inverters are connected in a loop. Then we have a op-amp based phase shift oscillator. We will see that for wireless application, we need very clean local oscillator signal. At the same time, the oscillation frequency is also going to be in gigahertz. So most of the time, we'll find that this kind of LC based oscillator only meet the spec for high frequency as well as spectral purity.